Hello, this is Jack Jackson, and we're going to continue from our last video where we had looked at the power rule for finding derivatives. In other words, the derivative of a basic power function. So our basic power function is f of x equals x to the n. Notice that's a variable base x and a constant power n, like for example x squared or maybe x cubed. And it turns out that the derivative is n times x to the n minus 1. And we proved that in a previous video, at least for all integer powers and also for power of 1/2. Later on, we'll prove it's true for all constant powers. So if you remember, we left off the last video by me giving you a little assignment to try out. And that was to take these functions, f of x equals x to the n, for these various different powers. So there's, a through n different problems here, different functions. And for each one, what I asked you to do was, first of all, before you graphed it, see if you could figure out what the shape of the graph was going to look like based on our earlier work. And then go ahead and graph it, say say using something like GeoGebra or some other graphing program on your computer or your graphing calculator. And then use the power rule that we just talked about to compute the derivative, and then see if you can figure out what the shape of the derivative should look like. So see if that agrees with both what the shape of the original graph looks like, and then also from that determine what the graph of the derivative should look like, and then also from the power function, from transformations of power functions where you put a coefficient in front, see if you can figure out what the graph of the derivative is supposed to look like from that. And then go ahead and graph the derivative on a graphing calculator or your computer software, and go ahead and see what that looks like. And then go ahead and do that for all these different ones. If you do all these, you end up getting all the different cases. And I asked you to do this earlier. If you haven't done it already, go ahead and just pause this video and work those out on your own. When you have that task finished, then come back and we're going to go over the solutions. Okay, so if you're still with me, I'm going to assume that you've actually done these yourself. So let's go ahead and look at this. And I've organized these into a little table here. And this table actually gives all the different examples. So the table is organized in rows depending on the size of n, and in columns depending on the nature of n in terms of if it's the rational number in the form p over q, what p or q are, whether they're odd or even. So we want to think of it as p over q where the greatest common divisor in p and q is 1. In other words, it's a reduced fraction for the power. Well, if that fraction is odd for P and odd for Q, it turns out that it's in the quadrant 1 and 3 for the original, has origin symmetry. It turns out that it has y-axis symmetry for the derivative. If it's even over odd, that's going to be quadrant 1 and 2 for the original. And it turns out the derivative will be odd over odd, so it's quadrant 1 and 3. And that if it's either irrational or odd over even, the derivative will also be odd over even or irrational, and it will have quadrant 1 and no symmetry for both the original and the derivative. So we can actually prove that if n is equal to p over q, where the greatest common denominator of the p and the q is 1, in other words, it's a reduced fraction, and we let f of x equal x to the n, that is x to the p over q. Note that f prime of x is n times x to the n minus 1 by our power function rule. So this would be n is p over q, so this is p over q times x to the p over q minus 1. 1 is q over q, so getting a common denominator and adding these together, that's p minus q over q for the new power. So if p and q are both odd, then f of minus x is the opposite of f of x, so f is an odd function and thus has origin symmetry. Since p and q are both odd, p minus q is going to be even. Therefore, this power is even over odd, and f prime of minus x is the same as f prime of x. F prime is an even function and has y-axis symmetry. Later on, we'll show that the derivative of any odd function is an even function. If p is even and q is odd, then f of minus x is the same as f of x, and f is an even function, and it has y-axis symmetry. Since p and is even and q is odd, p minus q is odd, and so f prime is now odd over odd. Okay, that means f prime of minus x is the opposite f of x, and f prime is an odd function, has origin symmetry. And again, later on we'll show that the derivative of any even function is an odd function. If p is odd and q is even, then f of x is only defined for positive values of x's, so the derivative should only be defined for positive values of x's. Notice this works out because in this case p minus q is odd, so we get odd over even again, so that's only defined for positive values of x's for the derivative, as you would expect. Similarly, if n is an irrational number, then f of x is only defined for positive values of x. And in this case, n minus 1 is also irrational, and f prime is only defined for positive values of x, again, as we expect. So notice that this shows out that if the original graph, any of them in this last column, all the graphs have origin symmetry for the blue original graphs, and their derivatives all have y-axis symmetry. And it's just backwards for the middle sign here, middle column here. All of these have y-axis symmetry for the blue graph, the original graph, and all their derivatives have origin symmetry on the red graph. All the ones in this first column right here, or this column, have our first quadrant only for both the first derivative and the original function. If you look at this line here, if we take a power bigger than 2 to start with, then when you do n minus 1, it will be bigger than 1. So the derivative and the original function will be concave up, increasing in the first quadrant. So you can see that here, and you can see some examples worked out. These are the ones that we're doing in our exercise earlier. And so you can see them, you can see the formulas here and the graphs here. You can pause this at any time if you want to look at these a little bit more closely. N equals 2 is a special case, y equals x squared, because its derivative will be y equals x, or y equals 2x, which is a straight line. Here n is 2, n minus 1 is 1. So we have concave up in the first quadrant, and then we have linear for the derivative. We could continue to have some that are concave up in the first quadrant, but the derivative is concave down. And we see that when the power n is between 1 and 2, then its derivative power, n minus 1, will be between 0 and 1. And so here's some examples of that, where we see the original was concave up in the first quadrant and increasing, whereas the derivative was concave down and increasing. When n equals 1, that's y equals x. We know this derivative is y equals 1, which is a horizontal line. So the derivative is positive and constant there. When n is between 0 and 1, the original graph is increasing concave down in first quadrant. You see here, and its derivative will be a negative number between -1 and 0. So it's going to have vertical and horizontal asymptotes decreasing concave up in the first quadrant. If the n is 0, then that's a horizontal line with a hole in the graph, and its derivative is also a horizontal line with a hole in the graph. It's y equals 1 for the original function, y equals 0 for the second one, but they're both undefined at x equals 0. If n is a negative number, then the power, then the original function is decreasing concave up in the first quadrant. Then n minus 1 is negative, which would make it decreasing concave up in the first quadrant, but it has a negative coefficient, so it's going to, whole thing's going to be flipped over the x-axis, so that now it's not in quadrant 1 anymore, but in quadrant 4 for the derivative. But we still have the symmetry things that we have over here. So here, the original function's in quadrant 1 only, the derivative is in quadrant 4 only. Here, the original is in quadrants 1 and 2, has y-axis symmetry. The derivative is in quadrants 4 and 2. Again, having origin symmetry. Here, the original function is in quadrant 1 and 3, having origin symmetry, and its derivative is in quadrants 2 and 4. So notice that the derivatives are not just straight power functions, but power functions with the coefficient, which is really just a stretch or compression vertically, along with, in the case of these last ones where the coefficient is negative, a vertical flip over the horizontal line, y equals 0, the x-axis. So there's some things about power functions. There's a lot of different graphs that come up, but the formula itself is pretty straightforward. And we've looked at some, you can look at these examples to see how this would work. So just taking one or two of these, here we go. X to the 8/5, the derivative is 8/5, and then x to the 8/5 minus 1. 8/5 minus 1 is 8/5 minus 5/5, which is 3/5. So it's 8/5 x to the 3/5, and of course that's what we see graphed right here, and so forth. You can check these all out against your earlier work. All right, power functions are really cool. There are lots of cool things that you can see in the graphs here. A lot of cool symmetry things to look at. Some hole in the graph asymptotes on some of them. Some domain issues to consider. Some are first quadrant only. We got some symmetry going on here. All of this kind of comes out of a really simple class of functions in one way. It's just a simple power rule. And of course, finding the derivative formula, it's pretty easy. Just take the old power, bring it out front, multiply by whatever is in the coefficient, and then subtract 1 from the power to get the new power.